And Justin Huntington and I are going to give kind of two related talks here. So if you're looking at the agenda and seeing two similar titles, it's because it's been part of a larger project and effort to try to develop an operational system for mapping evapotranspiration over California. And also want to acknowledge our collaborators at DRI, Justin and Charles and Andrew, as well as Kent Frame and Bekele Temesgen at the Department of Water Resources. And we've been lucky on this project to work with a number of different partners, DWR and ag. We've had the benefit of working with a number of growers across the state, from small family farms to some of the biggest agricultural operations in California. And then also want to acknowledge all the help and support we've gotten from our collaborators at CSU Fresno and USDA and UC Cooperative Extension, as well as UC Davis. And our work has been supported by the NASA Applied Sciences Program and the Department of Water Resources. So I think we've pretty well covered this slide here on threats to water supplies and water quality in California today. Some really nice talks on a number of these issues earlier. When we look ahead to implementation of SGMA once we form the GSAs, I'm sticking to when we form the GSAs. I think one of the key challenges will be estimating evapotranspiration and consumptive use accurately. And of course, consumptive use is one of the, through evapotranspiration by agriculture, it's really the key driver for changes in groundwater elevations over ag regions. Seeing some of the work that Jay showed earlier was really exciting, the potential to potentially apply GRACE data and downscale it to get higher resolution estimates. Even with that, we're really still going to need the estimates of consumptive use to try to get accurate estimates of withdrawals. And ET is really hard to measure accurately at field scales over large areas and long time periods. Rick Allen, a few years back, published a really nice review of different studies and looked at the typical errors. Hope that's legible from the back. Our lysimeters are our gold standards with errors at about 5%, maybe up to 15%. But those are really difficult and expensive to operate and maintain. You can do soil water balance calculations over larger areas or at the field scale, a Bowen ratio, eddy covariance. Those are all have accuracies in the range of 10 to 20, maybe 30%, but very expensive and difficult to maintain. So we look at remote sensing approaches, and we see for an energy balance approach, some of the previously reported studies, about 10 to 20% for expert users, maybe 5 to 15%. Remote sensing using a vegetation index, a reflectance-based approach, a little higher from previous studies. I think we've made some improvements on this, which I'll talk about in a minute, and some other measurement techniques. Importantly, when you look at the error for use of these techniques by a novice or someone who may not be quite as familiar or have as much experience using these techniques, the error goes up substantially. So what we have been working to produce for the state and for DWR, and also working with the State Water Resources Control Board, are some statewide maps with known accuracies and uncertainties that can be used as a baseline or reference data set. Another key challenge for California, as Joel mentioned, we've got 400 different crop types grown here. So a lot of the models that have been developed and tested have been applied in simpler agricultural systems with fewer crop types. So some real challenges in quantifying the accuracy of different remote sensing approaches for California, given the number of crop types as well as the number of crop rotations we have each year. Now, in talking with a number of partners, growers, as well as folks in cooperative extension, state water management agencies, here are some of the requirements that we've gathered for operational ET mapping in California. It's got to be field scale. So we need that kind of 30 to 60 meter resolution or finer if possible. It has to be cost effective. It can't cost an agency or organization millions of dollars a year. Ideally, we'd like to have a 10-year baseline period. If we can get to 30 years, that would be ideal. We really need that known accuracy. So even if there's a higher uncertainty, knowing what that uncertainty is for the estimates on a daily, monthly, and seasonal time step is critical. It's got to be timely, so we need to be able to provide data with a latency of ideally less than 1 month. Data needs to be open and transparent, and most importantly, we have to be able to ensure data continuity. So one of the key challenges with some of the thermal energy balance approaches is that right now they're dependent on one sensor, the thermal tier sensor on Landsat 8, the ETM sensor on Landsat 7, and both of those have had some hardware problems over the last few years. So we need to ensure that we have an approach that's robust over the long term. So what we've been working on, the teams at DRI, Cal State Monterey Bay, and NASA Ames, is to try to combine the strengths of different methods to ensure that we've got a robust, reliable data stream while also providing the best available data possible. So Justin in a few minutes is going to talk about an approach leveraging Metric, an automated version of Metric that's been implemented. And Metric has been a very widely used energy balance model. It's been used in across 22 Western states. It's It's been used in court cases in the Supreme Court of Idaho. So a really widely tested and robust model. But again, we have that dependency on the thermal measurements from Landsat 7 and Landsat 8. So we've also been working on implementing statewide ET maps using our Satellite Irrigation Management System. This is a reflectance-based approach. So it has the advantage of being able to pull data from multiple different satellites that are all collecting information in the red and near-infrared wavelengths. But it has some limitations in that it doesn't account for crop stress and it doesn't account for soil evaporation. So it's really looking at what we're mapping here with this approach is the basal crop ET, or the evapotranspiration under well water conditions. Now, for most of the crops grown in California, that turns out to be closely correlated with ET. And so what we're working on is using the strengths of these two different approaches to develop a robust system for ET mapping for California. So to explain a little bit more about how we apply the reflectance-based approach for mapping the basal crop coefficient, we start with the normalized difference vegetation index. This is a commonly used remote sensing index of vegetation condition. It allows us to track the crop canopy development for every field in the state. There are some really nice studies done by Tom Trout and my colleague Lee Johnson at NASA Ames that related normalized difference vegetation index to fractional cover for a wide range of crops across multiple years and found a really good consistent relationship. So we use that relationship to convert NDVI to fractional cover. There's then a whole library of studies that have been done relating fractional cover to crop coefficients. And Rick Allen and Luis Pereira put together a really nice synthesis of those studies in 2009, and then there's been additional updates since then for specific crop types. Once we have those basal crop coefficients, we pull in data from the spatial SIMUS product from the California Irrigation Management Information System to get the daily reference ET, and from that, then we can calculate the field scale daily basal crop ET following a standard FAO 56 approach. This is just an overview of the framework. Again, we're pulling in satellite data from Landsat and MODIS currently, reference ET data from the California Irrigation Management Information System, some site-specific information on crop types currently compiled from the county agricultural commissioners' offices across the state. We go through a whole series of processing steps, and then we're distributing the data products via web services, both through browsers and also to mobile interfaces. I should mention that SIMS was originally developed as an irrigation management support tool. So our primary objective is providing information on crop water requirements to growers and close to real time. And I'll talk a little bit about how that's being implemented. As we've done our accuracy assessments, we've also seen that we think the data is accurate enough, provides an accurate enough measure of consumptive use of that actual ET, that we can use it as a complementary method to the automated version of Metric that Justin is going to describe in just a minute. For every field in the state, this is an example of some of the data we've compiled from the county agricultural commissioners. We're really excited about the work that LandIQ is doing and looking forward to collaborating them on the statewide mapping. So we have even more accurate data on crop types. But we can use this information to actually apply crop-specific equations to convert the satellite-based information on crop canopy conditions to the crop coefficient that we can then use to estimate ET. Essentially what we're doing is applying the standard crop coefficient approach, but replacing the manually derived crop coefficient with an automated satellite-derived estimate or measure that's tracking the actual crop canopy development for every field in the state. As I mentioned, we're currently using data from Landsat 7 and 8. Retrospectively, we can also use data from Landsat 5, so that'll allow us to get a 30-year time series. We've been using the MODIS instrument on Terra and Aqua, which has a 250-meter spatial resolution, about 16 acres as our gap fill, looking towards the future now that we have Sentinel-2A data from the European Space Agency, which is a 20-meter resolution or about a tenth of an acre. We'll be switching this year and into the first part of next year to use that as our complementary measure. So between these 4 satellites, we hope to be able to get an observation about every 5 days once Sentinel-2B launches later this year. Just looking at what some of the ET maps look like for California. This is a time series from 2010 to 2015. This is the total annual ET here. Looking across the Central Valley, we can see the the impact of the drought and land fallowing on the west side of the San Joaquin. But as we get into these hotter, drier years, we also notice that where growers continue to produce crops, we see increased ET. Whoops, looks like 2015 already headed for the bar. So, so the data products are currently available through you can access them through a website. The website is also based on a web services architecture, so users can not just view the imagery, but also query data for time series or download time series for particular points. We do provide an application programming interface for integration with other web-based tools. So one of the things we've done is integrate the satellite-based measurements of fractional cover with the CropManage irrigation management decision support system that's been developed by Michael Kahn at UC Cooperative Extension in Salinas. This currently works for about 5 or 6 vegetable crops, and there's a project being led by Lee Johnson and in collaboration with the Almond Board to expand this to some perennial crops. So I'm really excited about this work, and some of the initial results from the field trials are showing very promising results for improving on-farm water management and irrigation efficiency. I've also integrated the data from SIMS with the ARC-CREST on-farm water use efficiency calculator developed by my colleague Lee Johnson at NASA Ames. And so this provides field scale calculations of the actual ET. It implements an FAO 56 soil water balance model to correct for the evaporation and stress. And in addition to providing the ET time series, it also provides measures of the consumptive use fraction and agronomic use fraction for just about every crop grown in California through a really nice, almost fully automated tool. I want to say a few words about the field validation, since that's been a major effort and something that I think is really important to do and to do rigorously. We have used an approach that relies on 2 independent methods for measuring ET in commercial agricultural fields. One, a water balance approach, where we're measuring precipitation, irrigation, drainage, and the change in volumetric water content, as well as a surface energy balance approach, either full eddy covariance or a surface energy balance residual method, where we're measuring the net radiation, sensible heat flux, and ground heat flux with a small flux tower. Some of the equipment we've deployed for the soil water balance measurements we've collected in commercial ag fields, we're typically measuring 8 to 16 points within the field at 3 to 4 different depths. So doing our best to capture spatial variability. Field sites, we've looked at as many of the major crops, either by economic value or by total water use as we can, about 14 different crop types. We have some ongoing studies with strawberry growers right now as well. Sites laid out roughly as a transect across California, and some of our initial results. So this is a comparison of the eddy covariance or surface energy balance residual and the soil water balance. I was really pleased. Remember, going back to the slide I showed earlier, the at-field measurements reported in the literature, the accuracy of these measurements, somewhere between 5 and 15%. I was expecting these measurements at a seasonal total would agree within 15%. Was hoping we'd get to close to 10%, and we're at 11.6%, with the soil water balance being typically about 5 to 8% higher than the eddy covariance. So pretty good agreement, and it increases our confidence in the accuracy of these field measurements. This is a comparison of the SIMS ET versus the eddy covariance measurement. As we'd expect, it's a little bit higher because, again, we're getting the crop water requirement. We're omitting the stress. So for the cotton there, the peach sites there, which are actually very heavily deficit irrigated once they harvest the peaches, as we'd expect, the basal crop ET is higher. When we correct using the ARC-CREST tool for stress, we reduce our error to 8.5%. So again, giving us confidence that we're getting the crop water requirement correct. When we look at the soil water balance versus the basal crop ET, we have more sites with those complete measurements over the season. Mean absolute error is still just about 14%, but this includes cotton and wine grapes and raisins and a number of crops that are deficit irrigated. When we just look at the well-irrigated crops, that error is reduced to about a little less than 9%, 8.7%, and a just very small bias of just 6%. And again, when we make the corrections across all crop types, including the deficit irrigated crops, with the ARC-CREST tool, we reduce our mean absolute error to about 7%. So really encouraged by the accuracy of these measurements, and we think that this is a promising approach that would be complementary to energy balance approaches, which we would still recommend as the default for estimating ET, but we think that this would still provide a suitable gap fill for operational ET mapping. So a couple of the strengths here. It's an extensible framework for satellite data processing. The basal crop ET really captures the biological demand for water for the plant, so it provides an estimate of the amount of water growers would need to produce the crop under well-watered conditions. Fully automated, and we can get the key data inputs, the satellite measurements we need from multiple satellites, Landsat 7, Landsat 8, Sentinel-2A, Sentinel-2B, potentially from commercial satellites or RapidEye if needed. It gives us field scale estimates that account for weather conditions and the observed crop canopy conditions, and we have an increasingly well-defined, well-known uncertainty with a very small bias. So some of the limitations, and Justin's going to talk about metric here in just a minute. We do still need to make additional corrections for soil evaporation and crop stress. At the field scale, we can do that with a water balance model. We're also looking forward to using some of the metric-based information to try to calculate crop stress correction factors, especially for the vineyards, places where cotton or peaches or other crops that have periods of heavy deficit irrigation are typically produced. One last limitation is that this approach right now is only applicable for agricultural land cover. So let me stop there, see if there are any other questions. Just few last comments. Currently porting it to Earth Engine to improve access and availability of data, working with UC Davis on their Delta intercomparison study for ET and contributing our data products. We have a number of ongoing demonstration projects too, looking at using this data and the benefits of using ET-based irrigation for irrigation management. So let me stop there and see if there's maybe time for one question. Thanks.
Thanks for your talk. So I have a couple questions.
Sure.
First is this the data that's going to be provided on DWR's GSP website?
No, not necessarily. So we will make the data available for evaluation by DWR. It'll be DWR's decision as to which product to select in the end. I don't think DWR has made the decision about which ET-based product they'll finally provide on the GSP website. I think that the results of the intercomparison study that UC Davis is doing with the Delta Water Master will be really important for informing those decisions.
Okay. And then my second question is, is there any chance that you can use NDMI, normalized differential moisture index, right, to look at water stress in crops so you don't have to do on the ground?
Potentially. I think that the better approach will be to look at find fields where we have consistent differences between the basal crop ET and the ET from an energy balance approach like metric, and find those consistent periods of stress, and from that derive the stress factors that we could apply to make the corrections. I think that would be more reliable and accurate than using an approach like NDMI. I think energy balance is much better at detecting the evidence of deficit irrigation than NDMI.
Okay, I think we should probably move on.
Right, great, thanks.
Thank you again.
Thanks so much.